Hi, this is Lisa Knight. This is the first of 4 lectures on momentum and conservation of momentum. In this lecture, we will learn what momentum is and how it's related to Newton's second law. The definition of momentum, given by the variable or symbol p, is mass times velocity. Anything that is moving and has mass has momentum. You can think of this as the object's moving inertia. When we learned about the first law of motion, the law of inertia, we learned that an object will stay in its state of motion unless an outside force greater than 0 acts on it. It's easy to understand the inertia of something is related to its mass, especially if it's at rest. The bigger something is, the harder it is to get it moving or to stop it. But also, velocity is important too. If it's already moving, the velocity contributes to its moving inertia as well as its mass. It is possible for a very big object and a very small object to have the same moving inertia momentum. The very small object would have to have a lot more velocity than the big object so that they would have the exact same mass times velocity value. For example, an 18-wheeler could be moving at 1 mile an hour and you certainly wouldn't step in front of it because you know you couldn't stop it. It has a large momentum because of its mass. But a bullet, which is extremely small, is moving extremely fast, and you equally would not step out in front of it because it would be very damaging and hard to stop. Even though it has a small mass, it has a super large velocity, giving it a very big momentum. Also, momentum is a vector, and whatever the direction of the velocity is the direction of the momentum. So when we describe the moving inertia or the momentum of something, if it's moving to the north at 60 miles an hour, its momentum or moving inertia would be very different than if the object was moving at 50 miles an hour to the south. Consider this. Consider changing the momentum of something. Changing the momentum of a bear that's dropping on the floor and bounces up. When the bear falls, it has a momentum of mv. And when it bounces up at the exact same speed, does it have the same momentum? Has it changed in momentum? Has it changed its momentum? Think about that. But first consider how Newton thought about momentum. When he first talked about his second law, he didn't even discuss mass times acceleration. Instead, he first defined what moving momentum was, momentum, m times v, and then he talked about trying to change the momentum of something. And what he realized is that that something was a force. And he said that in order to change the momentum of the object, you didn't just apply a force, you applied it for a certain period of time. And the rate at which the change occurred was called the force, that action that he talked about. So he said that force was equal to mass times the change in velocity over the change in time, which we now know is acceleration, and that's where we get F equals ma. But really, he talked about it in terms of force being the rate at which momentum changes, not just the change in momentum. And let me remind you, whenever we find a change, we mean that we're taking the final minus the initial value. So the change in velocity would be final velocity minus initial velocity. So he really stated his second law as the change in momentum over the change in time, or mvf minus mvi all over the change in time. So now let's think about this bear again. Is the change in momentum just mv, or is it 2mv? Let's think about it. The initial momentum of the bear is negative mv. Why is it negative? Because its velocity is in the downward direction. And remember, momentum is in the same direction as the velocity. The final momentum, when it bounces up, is positive mv because now it has a positive velocity. Its change in momentum is the final minus the initial, positive mv minus a negative mv, which means you add the two together and you get 2 mv. So it has doubled its momentum, right? It's doubled its mv. And it's positive, which means that the force that's causing it to move upward is upward. And that makes sense because the bear actually bounced upward. How would it do that if the floor didn't push it upward?